Hello everybody and welcome to another A-Level Chemistry exam question walkthrough. This time I'm focusing on the pH of mixtures and the calculations that are involved in that. This is obviously from the acids and bases topic. As ever, I'm going to be putting my thoughts in blue so you can see the thinking behind the questions, and then the answers are going to be in green. We're going to look at two questions, but before we look at the questions, there might be some of you who are quite confused about how to do pH of mixture calculations. So I've got something I want to share with you first. And so the thing I want to share is a flowchart that I've devised for calculating the pH of strong acid, strong base mixtures. So you can have a look at this yourself now, and I will refer back to this at the end once we've had a go at these questions. But you can use this to help you if you choose. I've picked two questions for us to look at that cover as much of the core content as possible, so I can give you lots of hints and tips along the way. This first question is about Brønsted-Lowry acids, and they dive straight on in by asking us for the meaning of the term Brønsted-Lowry acid, and this is just something that you need to remember, and it's not a lengthy answer. They've given us far more space than we need. We just need to say that Brønsted-Lowry acids are proton donors. And then another what is meant question. So what is meant by the term strong when describing an acid? And the answer there is it completely ionizes to give hydrogen ions in water. Remember, that's what acids do. They are proton donors and they ionize when you put them into water, and strong acids do this completely. And then we go on to a calculation question. We have been given some details about a strong monoprotic acid, and monoprotic means that there is one hydrogen ion that can be donated per acid molecule. We don't actually know what the acid molecule is, but we know all the details that we need, which is that this is a strong acid. And the acid can be summarized as being HA, where H is that one proton that can be donated, and it's a strong acid, so this is an irreversible reaction. It's going to go through to completion. That proton is going to be donated, and the rest of the acid is going to be the negative ion. We've been asked to calculate the pH. We've been asked to give this to 2 decimal points, so I always encourage you to put yourself a little reminder down there that we need to have 2 decimal points. And since we're calculating a pH, the final thing that we're going to have to do is negative log of the hydrogen ion concentration, and that means that the first thing that we're going to do is work out what the hydrogen ion concentration is. Now, on this occasion, we've been given a moles of hydrogen ions and we've been given a volume, and since moles equals concentration times by volume, we know that concentration will be equal to moles divided by volume, and so our moles are 1.45 times 10 to the minus 3. Our volume is 25 cm cubed, which we need to make a little note that we need to convert that into dm cubed by dividing by 1,000, because then we put that into the bottom of our expression. And when we run that calculation, we get a concentration of hydrogen ions of 0.058 moles per decimeter cubed. And then when we do negative log of that value, we get 1.24 to 2 decimal points. And that is our second mark. So 1 mark for the hydrogen ion concentration and 1 mark for the final pH. And then the last part of this question is asking us to calculate the pH of the solution formed after the addition of 35 cm cubed of a particular concentration of sodium hydroxide and then 25 cm cubed of the monoprotic acid. So I'm doing slightly different sort of underlining just so I can see the ownership of each sort of set of numbers for the sodium hydroxide and for the monoprotic acid. So when you mix an acid together with a base, there is the core concept that one of those two things will be the limiting factor and the other one will be in excess. And the one that's in excess won't get used up, and so there will be some hydrogen ions or some hydroxide ions left over, depending on which thing is in excess. And so our first job is always to work out the moles of all of the chemicals involved. And so we've been given a concentration and a volume of sodium hydroxide. So we need to first of all work out the moles of sodium hydroxide by turning that 35 cm cubed into decimeters cubed, so 0.035 dm cubed. And then doing moles is equal to concentration times volume for the sodium hydroxide, which gives us an amount of sodium hydroxide in moles of 5.25 times 10 to the minus 3. We already know from the previous question that there was 1.45 times 10 to the minus 3 moles of hydrogen ions, so no extra marks for recognising that here, but it is important. And since sodium hydroxide reacts with this monoprotic acid in a 1-to-1 ratio, then we can see that the hydroxide ions are going to be present in excess because the moles of hydroxide is greater than the moles of the hydrogen ions. So we need to calculate the amount of excess that there is, and so we subtract the hydrogen ion moles from the hydroxide ion moles, and that gives us 3.80 times 10 to the minus 3 moles of hydroxide in excess. Now, I said it was a 1-to-1 reaction ratio, and obviously you can just remember that reaction ratio if you're able to, but we can actually work it out as well, because in sodium hydroxide, we can see from the formula that there is one hydroxide ion. And we can also see from the formula that I drew earlier, the HA, that there is one hydrogen ion per molecule. But also we've got the clue that it's monoprotic, and so that's going to be one hydrogen ion for sure. And then if you remember that any neutralization reaction can be reduced down to the ionic equation, H plus OH minus turns into water. So you need one hydrogen per hydroxide ion. So since these two molecules have got one of each of them respectively, then the reaction ratio will be 1-to-1. So we've got 2 marks of our 5-mark question, and now comes the third step, and I've overlooked something that needs to come into play now. They've told us the ionic product of water at 298 Kelvin is 1 times 10 to the minus 14, and that is a big clue that the hydroxide ion should be in excess, because what we need to do now is work out the pH of the leftover hydroxide ions. And so to do that, there are 3 steps, and as I have said previously, if we're working out a pH, the final step needs to be the negative log of the hydrogen ion concentration, which means the penultimate step is to work out what the hydrogen ion concentration is. Now, since this is a strong base, because we've got hydroxide ions left over, we need to use the Kw expression, which is Kw is H plus multiplied by OH minus. And so that rearranges to give us the hydrogen ion concentration is Kw divided by OH minus, and we don't yet have OH minus. We have got Kw, but we've not got OH minus, which means the thing that we need to do next is work out what the OH minus concentration is. So it's a concentration, so we're going to do moles divided by volume to get that concentration. We know the moles because we've just worked it out, 3.8 times 10 to the minus 3. What we don't know is the volume yet, but the volume of the sodium hydroxide was 35, the volume of the acid was 25, so together that gives us a volume of 60 cubic centimetres, and so we need to put that into cubic decimeters by dividing it by 1,000. And then when we do that, we get a hydroxide ion concentration of 0.0633 moles per decimeter cubed. Then we take that hydroxide ion concentration and plug it into the Kw expression that we've already rearranged. And so we've got our 1 times 10 to the minus 14 divided by 0.0633, which gives us a hydrogen ion concentration of 1.58 times 10 to the minus 13. And then when we take the negative log of that answer, we get a value of 12.80 for our pH to 2 decimal places. Okay, so on to the second question about mixtures of acids and bases. We begin by looking at nitric acid, HNO3, which is a strong acid, we've been told, and then ethanoic acid, which is a weak acid. And they've asked us to write an equation to show how ethanoic acid, the weak acid, behaves as a weak acid in its reaction with water. Now, you've actually got 2 options here. because one option is that you just don't show it actually reacting with water, you show it behaving as a weak acid, and that would always be my preferred option, because all you actually need to do here is show the ethanoic acid dissociating. So ethanoic acid, we've even been given the formula already. It dissociates into a hydrogen ion, of course, because that's what acids do, and the conjugate base, which is the ethanoate ion, as I've shown there. The trick here is this is a weak acid, which means that you cannot show the regular full arrow. This is only partial dissociation, so we need to show it as a reversible reaction like so. And that's actually all that you need to do to get the 1 mark. However, what you could do instead is you could show this as a reaction actually literally with water. And to do that, what you would do is you'd write the formula of ethanoic acid again. You would show it adding with water, like so. Then it's the same reversible reaction symbol, and we make the same conjugate base, only in this form of equation, we show the water has gained the proton to make the hydroxonium ion H3O+. Either of those is absolutely fine. I think the first one is much, much easier. Then part B is an interesting question because it's saying that ethanoic acid can react with pure nitric acid, and in this situation the ethanoic acid acts as a base. Remember, when acids react, you always get an acid-base equilibrium, and the stronger acid is the species that will donate the proton, and the weaker acid is the species that will accept the proton. This comes in again in the reaction of benzene with the conch sulfuric reacting with the conch nitric acid. On that occasion, the nitric acid actually acts as the base. But here, the nitric acid is far stronger, and so it acts as the acid. And so all that we need to do to start this answer off is write out the formulae that we've been given of ethanoic acid and nitric acid, like so. And then we need to show what that's going to turn into. Now, the nitric acid is going to act as the acid, and the ethanoic acid is going to act as a base. So quite simply, the nitric acid needs to be rewritten without the hydrogen ion, and so this would now have a negative charge of 1 because it's donated its H+, and then the ethanoic acid would accept that proton, and so we rewrite that formula. It looks a little bit funny. We rewrite that formula as CH3COOH2. Obviously, that's now going to be positively charged because the proton has been gained by the ethanoic acid. Now, the next question is a good question because it's a little bit more confusing than it seems like it should be at face value. We've been given some information about the nitric acid. We've been given a volume in cm cubed and a concentration, and we've been asked to calculate the pH of the solution formed after 50 cm cubed of distilled water are added to this beaker, and we've been told to give this to 2 decimal points, so let's write ourselves a reminder down there. So the most common wrong answer here would be for the people who just dived straight in and used this concentration of the nitric acid and just took the negative log of that value. And at face value, that looks like that's what you can do. Remember, it's a pH, so clearly the last thing that we're going to do is negative log of H+. We've already been told that the nitric acid is a strong acid, so that means that the nitric acid concentration is going to be the same as the hydrogen ion concentration. However, because we're adding the water, the effect that that has is diluting the acid. And so what we need to do is find the new acid concentration, which will be the same as the new H+ concentration because it is a strong acid. So there's 2 ways of doing this. You can go down the moles route or you can go down the proportion route. They'll both, of course, get you the same answer. So let's do the moles route first. So the moles route would say, right, well, how many moles of nitric acid did we have at the beginning? And so moles is concentration times by volume. So 0.0125 multiplied by the volume of nitric acid in dm cubed. So remember, that's going to be 0.1 dm cubed. And so that will give us 0.00125 moles of nitric acid. And then what we need to do is we need to work out the new concentration because the volume has gone up to 150 cm cubed, or 0.15 dm cubed. So the new hydrogen ion concentration is going to be 8.33 times 10 to the minus 3 moles per decimeter cubed. And then we need to negative log that value, which gives us a pH of 2.08 to 2 decimal points. Must be in 2 decimal points. Now, there is an alternative method to work out that new concentration of acid, or new concentration of H+. And so the idea here is the original volume was 100 cubic centimetres. We've added 50 cubic centimetres to it, so the new volume is 150 cubic centimetres. So the concentration will have gone down as a result, because we've got the same moles of acid that we started with. We've just added water to it. And so the new concentration will be 2/3 of the original concentration. And that works on the principle of proportions, because the concentration times by the volume before we started mixing will be equal to the concentration times by the volume once we've diluted it. I'll just do a little subscript D for diluted. And so what we can do to work out the new diluted concentration is divide both sides by the diluted volume. And so what we're left with is the diluted concentration is the original concentration multiplied by the original volume by the diluted volume, like so. And so in terms of crunching the numbers in, the conc was 0.0125, the volume was 0.1, the new volume was 0.15, and so we get our hydrogen ion concentration this way instead. Personally, I prefer the method that I showed up in the actual question space, but it is totally up to you, whichever you want to use. And then the final question on this page is a 6-mark question, and that will either fill you with fear or, as I would prefer, make you anticipate getting 6 straightforward marks. Not easy, but the routine that we're going to follow will be exactly the same as on the previous page. So just like before, we've been told we've got a concentration and a volume of one chemical, which I'll underline in blue. We've got 40 and 0.012, and that's sulfuric acid. I would encourage you, when you are kind of decoding the question, to work out the formulas of these substances, just in case there's anything intriguing about them. And there is here, H2SO4 is the formula of sulfuric acid. And what that means is that it is diprotic. And so what that means is, for every mole of sulfuric acid, there will be 2 H+ ions. And so, as inevitably we will, we're going to work out the moles of sulfuric acid. We're going to therefore have to work out the moles of hydrogen ions as well, as we'll see in a minute. And then the sodium hydroxide, we've also got a volume and a concentration for. And sodium hydroxide, nice and straightforward, that one, NaOH. There's only one hydroxide ion per molecule. So then in terms of the marks, the first marks here will be for working out what the moles of each of these two substances are. So concentration times volume for both of them. So when we work that out for the sodium hydroxide, we get 5.4 times 10 to the minus 4, or 5.40 to 2 decimal points. And then when we work out the moles of sulfuric acid in the exact same way, conc times vol again, we get 4.8 times 10 to the minus 4. This is where we need to acknowledge this diprotic structure, because the moles of the hydrogen ions will be twice as much as the moles of the sulfuric acid. And so we need to double the moles that we've calculated. And then it's exactly the same as in the previous question, where we need to work out, well, which of these is in excess? And we can quite clearly see that the hydrogen ion moles, 9.6 times 10 to the minus 4, is bigger than the sodium hydroxide moles, 5.4 times 10 to the minus 4. So we need to subtract the moles of sodium hydroxide away from the moles of hydrogen ions to give us our excess. And when we do that, we get 4.2 times 10 to the minus 4 excess moles of hydrogen ions. And so that's our 4th mark out of the 6, and we need to remind ourselves that we've been asked to calculate a pH, which means the final thing that we do is negative log of hydrogen ion concentration. And it's worth pointing out that this is hydrogen ion concentration, and because I've taken the care to put the units in, I'm reminding myself that what I've calculated here is the moles. And so step 5, which is why I've left this little gap, is to work out what the hydrogen ion concentration is now. And so since moles is conc times vol, concentration is moles divided by volume, the new volume, the combined volume. So the moles is what I've just calculated. The combined volume is the 50 cm cubed plus the 40 cm cubed, so 90 cm cubed, which of course is 0.09 dm cubed. And so once I've run the numbers there, this gives me a hydrogen ion concentration of 4.67 times 10 to the minus 3. And then last of all, we negative log that value, which will give me a pH of 2.33 to 2 decimal places. So I said we'd refer back to this flowchart once we'd finished. And so just to remind you then, this is your guide to calculating the pH of strong acid, strong base mixtures, and it will never steer you wrong. So first of all, you need to calculate the moles of acid present in the mixture and then calculate the moles of H+ ions. Make that a routine to actually make that declaration. I've got this many moles of acid, so therefore this many moles of H+. And that's particularly relevant for diprotic acids such as H2SO4. Similarly, you will have another mark for working out the moles of base that's present and therefore the moles of hydroxide ions. Now, both of the examples that I used involved sodium hydroxide, and that's by far the most common base involved, and that's only got one hydroxide ion per sodium hydroxide mole. However, it's perfectly possible you could have something like magnesium hydroxide or barium hydroxide, and in that situation, both of those have got 2 hydroxide ions per mole of the whole formula. Then, once we've worked out the moles of both of those ions, we need to work out which one is in excess, in other words, which one is the largest, and once we've decided which is the largest, we subtract the smallest away from the largest to work out how many leftover moles we've got of hydrogen ions or hydroxide ions. And then the path that we take after that depends on which of the 2 ions was in excess. And it is far easier if the hydrogen ions are in excess, because what we do then is we work out the new hydrogen ion concentration by doing the excess moles divided by the total volume in dm cubed, and then of course negative logging the hydrogen ion concentration after that. It's a little bit harder if the OH- ions are in excess. The first thing that you do though is the same. You do the excess moles divided by the new volume. Then though what we have to do is an extra step, because we just worked out what the hydroxide ion concentration was. We need the hydrogen ion concentration before we can negative log it, so it's Kw divided by the hydroxide ion concentration. We will probably get clues that we're going down this pathway if they give us the Kw value at the start of the question. I don't think I've ever seen a question where they've given you Kw and actually you went down this path and it was completely false and unhelpful information. But there is always a first time. Okay, that's the end of this video. I hope it was useful. I'll be back again soon with a video about buffer pH, so don't forget to look out for that. Goodbye.